So I've decided to use you guys as guinea pigs. This is my first presentation in Prezi. So I'm either going to make you all terribly seasick or it's going to work. So I've decided to try to get away from using PowerPoint. But since I interviewed so recently, most of you guys are pretty familiar with what I have done. And for those of you who aren't, I can just give a little brief rundown of my career thus far, short. So I started research in Antarctica as an undergraduate at Hamilton College and went down to Antarctica in 1995 as an undergraduate. My task was to take sediment cores in the Bransfield Strait at the tip of the peninsula and to look at the Holocene climate signals in those cores. And that cruise goes down as the worst cruise in history according to NSF because they had two warring PIs, Larry Lauver and Gary Klinkhammer, and when one of them went to bed, the other one would decide to go somewhere else. So we spent most of our cruise going back and forth into the Scotia Sea. So that was an interesting experience. But then I went I published my undergraduate thesis at Hamilton College, and it's now my second most highly cited paper, which is ridiculous. But it was basically on Holocene climate change in Lallemand Fjord on the western side of the Antarctic Peninsula. So I've been working in Antarctica for a number of years. I went and did my PhD with Jim Kennett at Santa Barbara, and I worked more on the long-term evolution of the Antarctic cryosphere. So how did the ice sheet develop over on million-year timescales? And in particular, I looked at the Middle Miocene, but now I have research looking at the Eocene, so 33.4 million years ago, 16 to 15 million years ago, and the stuff I'm going to be talking about today is more recent stuff. And apparently you have to start at the beginning of a presentation here. Okay, I'm at the beginning now. So some of you have seen this slide before, but we know that Antarctica is particularly important in the global climate system. Basically, the Antarctic ice sheets, both east and west, essentially control global sea level during the Holocene. And processes going on around Antarctica actually influence ocean ventilation and carbon cycling, especially in the subantarctic. So what happens in and around Antarctica actually really matters. And oftentimes what you'll see in data sets is you'll see this whole region of the Southern Ocean ignored. We don't really understand, I think that's safe to say, that we really don't understand the details of a lot of the processes that are ongoing around the Antarctic margin. And so I've been involved in work that's trying to understand these processes both in the modern as well as in the past. So what we know now is that Antarctica is experiencing atmospheric warming, and this was a paper from 2009 from Eric Steig in Nature that suggested not only was the West Antarctic warming, but also the East Antarctic was warming, and this was significantly different from previous investigations. So another paper that came out a couple of weeks ago suggests that this warming is even more dramatic. So we're seeing atmospheric warming around Antarctica. And the question is, how is this influencing the ice sheets, ice shelves, and the Southern Ocean system? We've also seen that the Southern Ocean is warming pretty dramatically in the last 50 years. And that those warmer waters are now propagating northward into the deep Pacific. Oh, jeez. Sorry about this. Etc. And we've seen some major changes in the ice sheets and the ice shelves, and the most dramatic and the most often cited is the collapse of the Larsen B ice shelf and that happened in a matter of days in 2002. And so we're trying to understand that process. Why did it collapse? Had it collapsed previously in the past, or was this an unusual event? So a lot of what I do is look at the marine sediment record from Antarctic and Southern Ocean cores. And in the Paleo Lab, I do both Antarctic research, which I'm focusing on, but we also have projects going on in the Arctic and in the North Pacific. And also using both the ocean drilling program and piston coring on the U.S. Antarctic program ships, the Palmer and the Gould. And you can get beautiful sediment records that contain details of climate change. This is the Palmer Deep core I'll be talking about over the Holocene. And the reason I didn't have a title for this is because we were actually at Florida State, Michelle and Tasha and I, earlier this week sampling some of these sediment cores that I'm going to be talking about today. So in terms of the Paleo Lab contribution, what I do is I look at mostly sea surface temperature change. So how does the temperature around the Antarctic margin change through time? And does that have any relationship with things like circumpolar deep water upwelling onto the shelf, with atmospheric warming, with changes in storminess? So we're looking for and developing paleotemperature proxies. The most useful, it seems, right now is TEX 86, which looks at the lipids of marine archaea. And so this is a picture of us drilling Palmer Deep in 1998. I was on the Gould at that time. This is the JOIDES resolution off of Palmer Station. And here's the core that we collected from there. And I won't get into the details of this. Prezi is not going seamlessly, but here we go. So let's talk about some of the work that we've done on the Antarctic Peninsula. Are you seasick yet? So this is one of the most rapidly warming areas of the globe. So we've seen upwards of 3 to 5 degrees warming, and I picked 2007 to just as a representative year, but you could choose any year. And the peninsula is warming most rapidly in all of the southern hemisphere. We've seen reduced sea ice extent and surface ocean warming in this area. Again, ice shelf collapse and ecologic changes. So this was actually part of the project that I'm working on now called Larissa, where they used a yo-yo cam and deployed it into Palmer Deep, where I worked on the sediment core. And what they found was these king crabs just absolutely inundated the basin, and they had never been seen before at that latitude. And so something is going on that's changing the conditions around the western Antarctic Peninsula. And there are a lot of reasons for this. One may be the increase in circumpolar deep water that's upwelling on the shelf, and that water mass is very, very warm. So temperatures at depth in this area tend to be around 2 degrees. Okay, so this is a slide that's sort of a continuation. When I gave my my talk for my interview, we had a paper that was going into press in Nature about the sea surface temperature record in Palmer Deep, shown here in the purple star and the blue line. This was our TEX 86 record. So here's age from 14,000 years ago, so deglaciation, to present. And what we showed was a general cooling trend until about 2,000 years ago, when we have an increase in warming. And what we said was this was related to teleconnection with the tropical Pacific. So at a time where you had increased actually La Nina events, we were getting warmer temperatures on the Antarctic, western Antarctic Peninsula. And that is a relationship that we've seen presently. And so this was a prediction that we made, and we said that if that our hypothesis was correct, then the eastern side of the Antarctic Peninsula should show a cooling at this time, because right now there's a dipole in the temperature records on the east and the west, and when you have a La Nina event, you have warmer waters in the western Antarctic Peninsula and cooler surface waters in the eastern side of the peninsula. And so this was a record published last year, an ice core record from James Ross Island by the British, and this is their record of temperature and the temperature anomaly for the Holocene. And so they also see this warm early Holocene, cooling, and then instead of seeing a warming here, they see a cooling, which is exactly what we predicted. So in terms of an update to my previous work, it seems as if one of our hypotheses is actually gaining some strength. And that was really nice to see. It was also the easiest time I've ever had publishing in Nature. I didn't have to do anything. My data showed up. So what are we doing now? What's new? I was gone for pretty much the month of November on the Lawrence Gould. So these are two the U.S. Antarctic program ships, the Palmer, which is the icebreaker, and the Gould, which is the ice-strengthened vessel. And this is from Punta Arenas. And what we did was we went down to Palmer Station, and we were going to take sediment cores and do some water sampling, and you will hear about what happened next. Basically, our objectives were to recover cores to determine the timing and the retreat of the Antarctic Peninsula ice sheet. So basically, those of you who are familiar with Palmer Station, there used to be a big ice dome over that area. And there were glaciers and ice streams that flowed out both to the west and to the east. And understanding when that ice dome collapsed is really important for the timing of deglaciation during the last 14,000 years. And there are two sort of hypotheses. One is that deglaciation is driven by melting, so increased circumpolar deep water and temperature, heat around the margin. And one is that you actually increase sea level during meltwater pulse 1A, and that the sea level rise then destabilizes the ice sheets and ice shelves around the Antarctic margin. And so we're trying to understand what caused deglaciation. We also needed to install and repair some GPS stations along the western side of the peninsula. And these are recording the isostatic rebound that's related to the collapse of the Larsen B ice shelf. And in some of these sites, we're actually seeing uplift of 10 centimeters per year, which is pretty crazy and real. And so this is stuff that Gene Domack, my undergraduate advisor, is working on, and Tim Dixon is actually getting involved in this as well. We also, sort of the third and final thing was to look at the archaeal populations in Palmer Deep and try to calibrate the Tex 86 paleothermometer. And we're going to be working with Maya's lab to understand the populations of the archaea both in the water column as well as in the sediments. So those were our three objectives for this cruise, and then we encountered some problems. So basically the wind started to blow from the south, and what happened was all of the fast ice in Graham Land to the south got pushed to the north, and what we ended up with was something like this. And here's a picture of Anvers Island, off the western side of the Antarctic Peninsula. Here's Palmer Station here, for those of you who are familiar. Graham Land is down here. And all of this white is sea ice. So we came in through the Gerlache Strait, and that was that picture I just showed, nice open water. And we got to here, and it was a nightmare. And the sea ice was just incredibly bad, worse than anyone had seen it since the 1980s. And one of the ideas is that because there's so much meltwater coming off these glaciers, you're actually forming sea ice at higher temperatures. And so the fast ice down here in Graham Land was a lot worse than usual. And then we got this big storm. And basically all the ice came up and it pushed against Anvers Island. And so the pressure increased and increased and increased. We were forming pressure ridges, which made for a pretty dangerous situation. This could have been us, the Endurance. So we decided to hang out at Palmer Station, and we were there for 5 days under beautiful, non-windy conditions, and the sea ice was absolutely terrible. And at one point we tried to leave, and we came back. And let's see if that actually works. And if it doesn't, that's okay. Some of you have seen this before, but this is a video of basically a time-lapse photography video of the Gould. So I was on the ship coming into Palmer Station, obviously accelerated. Oh, sorry.
Where's the bar?
This was actually taken from, well, no, this wasn't taken from the bar. This was taken from the kitchen. The bar is back. It doesn't have as good a view of us coming in. So we're breaking up ice. NSF absolutely freaked out about this video because you're actually technically not supposed to do this with the Gould. It's not rated to break ice like this. But we did it anyways because we wanted to get into the harbor here to be protected from the pressure. And just when you think we're at the pier, we're not.
Rang the bar.
Yep. I won't show you the whole video. At the end, you can see all of us running off and running up to the bar. Oh. We've got one more maneuver.
Maybe he's just a bad parallel partner.
Yeah, you know, you would think, but I don't know. The donuts are pretty good. There's one coming up here. Yeah, that was me driving. Anyone who's ever driven with me knows that this is probably pretty accurate.
I hope you don't always drive like this.
I grew up in Boston. I always drive like this, if not worse.
Damn! It's nice to see that a captain of the Gould, though, has got a little piece on.
It's Ernest. Ernest Stelly. So, yeah. So the captain on this cruise was actually the cook on the Palmer for a long time. So I don't know what that says. But anyways, you get the point. Ernest Stelly. Yeah. So anyways, to continue with the science part, after 5 days and finishing all of Palmer Station's beer, we actually got out and started doing some work. And our first targets were to take some sediment cores in drifts. So there's a nice sediment drift here with like probably 80 meters of sediment. And what we wanted to do, this is a grounding line feature. So the ice shelf was grounded here. And there was probably an ice shelf that came out over this basin. And what we want to do is we want to date this grounding line and determine when, this feature was active, and so when the retreat actually happened on the shelf. So we took some sediment cores, and they were supposed to be at Florida State, and that was one of the reasons why we went up this week, and they haven't arrived yet. So the Gould is actually pretty capable of doing a lot of really great science. It's an underutilized vessel. And so we took 12-meter jumbo piston cores at several sites, and this was one of the ones in the Gerlache. And we tagged into some of the lower deglacial reflectors, so we've actually recovered our target, which was pretty neat, and I can't wait to open up those cores. We also, so this is one of the GPS station at Dutier's Point that we installed and upgraded. But we also did a lot of casting coring, so that's Brad Rosenheim, for those of you who know him. He also works in the Gulf. He's at Tulane, and Gene Domack sampling the casting core. So after a frustrating beginning to the cruise, we actually ended up getting a lot of really great sediment cores that we're going to work on here, as well as up at Hamilton and Tulane. So the other things that I've been doing since I got here is learning how to use Prezi. Actually, I learned that yesterday. Is I initiated a project in Prids Bay that's actually been recommended for funding by OPP. However, they still are holding back 20% of their budget, 10% for the sequester if it happens, and also for the continuing resolution. So what they did was they funded all of the ship-related projects first, and they're holding off. So we'll see. I still haven't heard. But this project that I proposed was to look at the late Quaternary glacial history of Prids Channel in Prids Bay, Antarctica. And so we wanted to do this because we wanted to evaluate the timing, the speed, and the retreat of the Lambert glacial system. And the Lambert-Amory ice shelf system is one of the largest that drains East Antarctica. So it drains 15% of the East Antarctic ice sheet. It's also grounded below sea level. So it is really sensitive to any sort of changes in temperature. And it's one of the places where you can actually see a record of sediments younger or older than the last deglaciation. So what we want to do is we want to see the timing and speed and style of retreat, and we also want to look at how circumpolar deep water intrusion actually, when it happened in the late Quaternary. And so we took some cores in 2001, and I was on this cruise. It was from January to March 2001. We left from Hobart. We got back into Cape Town, and we cored the Prids Channel in front of the Amory ice shelf here. So these are the cores that we'll be working on. Circumpolar deep water comes up onto the shelf here and is modified, and then sometimes forms Antarctic bottom water depending on the year. We don't know a lot about this area, but we do know that Prids Channel is a deep that is actually situated between two moraines, and these systems bring in material from the East Antarctic ice sheet. And we took these sediment cores, 25-meter sediment cores, actually these are only 5-meter, in 2001 from the Palmer. And this is an example of some of the cores that Michelle is going to work on for her master's thesis, and these were the ones that we sampled this week. And basically what we can see is that we have these diatom-rich intervals, and then all of this glacial marine material in between. And we've tried to date these diatom intervals previously, and it looks as if they're older than last glacial maximum. And so the question is, do these diatom intervals represent times when the Amory ice sheet shelf was landward of the core sites? And so these diatom intervals actually suggest that the East Antarctic ice sheet was a lot more variable than we previously thought. A lot of times we kind of think of it as this big ice block that isn't very dynamic, but it could be very dynamic. And these cores actually are some of the only cores that record these last glacial, interglacial, or stadial, interstadial events. And so that's why these are attractive and we're targeting them. So hopefully Michelle can get some better ages. We're doing some diatom-bound work and some other radiocarbon work, as well as some ramp pyrolysis work with Brad Rosenheim. And we should be able to get better dates on these intervals. And we're also thinking about doing some optical simulating luminescence work. So that's a new project that we literally started this week. And another project that we have going on is we found out that we have a cruise that was funded to go to Totten Glacier, and in 2014 in January. And so Totten is pretty remote. It's unsurveyed, and it's also unstable in that it's grounded. It has a marine grounding line. And so basically, because this would be similar to Prids Bay, that we would see this potential instability through time. Totten drains 1/8 of the East Antarctic margin of the East Antarctic ice sheet, which is an equivalent to 6.9 meters of eustatic sea level. So for this cruise, we're thinking about what are the causal mechanisms for rapid thinning of the Totten Glacier? What does the record, the marine record look like? This is an area where actually subglacial Lake Vostok drains and has drained in the past. So there are these eucalypts, we think, based on some of the surveys that we've done farther offshore. And we also want to look at the marine sedimentary record to see if there are any sort of similarities to the Prids Bay record, to see if we can get these sort of a better idea of how the margin fluctuates through time. And so this cruise is going to be a bunch of physical oceanographers, so Alex Orsi, John Blankenship, me, and then Amy Leventer and Jean Domack doing the marine geology. And we have the Texas group led by Sean Gulick doing seismic, multi-channel seismic. So this was determined to be a high-risk, high-reward project by NSF. The main concerns about the reviews were, are we going to be able to get there? This was a picture of the area from 2001. We were not able to get there because the katabatic winds were so strong that we couldn't hold station. So that is a concern. There is the CTD blowing in the wind. So we've just done the seismic sea trials for the multi-channel system off of Chile, and it looks really good. We're getting pretty amazing data. So if we can get that data quality in the ice, we'll be lucky. But this is a new streamer that NSF has purchased for this project. So that's pretty exciting. And I think that our main concerns are, will there be ice? Yes, probably. And will the katabatic winds be bad? Yes, probably. This is what it looks like when we were there last time. So we're going to be taking sediment cores, and hopefully those will be projects for my future students. So we have 3 ongoing projects and more to come, and doing a lot of climate, both recent and long-term research in the Paleo Lab in the Antarctic. So thank you all, and I'm glad you suffered through my first presentation. I'm not sure if I like it, but we'll see.
Not Saturday yet. But our what? All right then. Next, we'll have Professor Luis Garcia Rubio, Professor Emeritus of Clinical Oceanography, and he has started an excellent company a couple of years ago, and let's hear his adventure in different work.
So, thank you. Good afternoon, everyone. It's always great to have be the speaker after the break, because when you come into the room just before the break, everybody's leaving, and then you have a justification to think that it's not because you just came in, right? So I've been working for a number of years in trying to translate technology that was developed here at USF, and particularly that took the last stages of development here in the College of Marine Science. And it's an interdisciplinary approach. So I'm going to sort of speak right now from the point of view of the company that is being developed, and the technology, the science, and the projects that are associated with it. And we hope this year that we will be able to bring some of our prototypes in the more fundamental science to be done at the university. Because you can only go so far in terms of resources and scope within a company, but it's important to continue to develop the science. So if you have questions as we go along, please feel free to ask them. So the name of the company is Claro Scientific, and we are located right here in 4th Avenue. Do you know where the blood bank is? Florida Blood Services. We're co-located with them. They are our incubator, because many of the applications that Claro is pursuing have to do with health and with the application of sensing technology to health-related problems. So the objective of the company is to commercialize systems for testing, research, process control using what we call an optical profiling technology. And I'll elaborate on that. Just to give you a sense of scale, keep in mind that we're going to be talking of entities, discrete entities in the order of nanometers all the way to microns. Right? And that encompasses not only many industrially related processes, emulsions, droplets of oil in the sea, but also includes cells, viruses, and tissues. So what I'm going to be talking about and what the thrust of the commercial development and the research program has to do with optical sensor development for the characterization of micron and submicron particles. As I said, the scale is from nanometers to microns. In fact, this year we are publishing a series of papers on applied spectroscopy that emphasize on the fundamental theories behind the analysis. Okay, so, we need to define a problem. What is a problem? And the problem is both from the scientific and from the commercial point of view, because both are customers with different objectives. So the need is to acquire and processing complete characterization data, or as complete as possible, for macromolecules, nano size, in particles, all the way to cells, in real time, for research, process development, and production environments, and as well environmental science. So when you think of the problem in that perspective, you have to ask yourself the question, what do I need to do to accomplish the measurements? And well, the first thing that comes to mind is portable laboratories. How do we implement that? The second thing that comes to mind that is very familiar to everyone here in marine science is miniaturized autonomous systems, because you want to take them everywhere. The other thing that becomes relevant is we're not going to do with just measuring a single variable. We need to measure more than one variable, and that means that we need to have multi-purpose and or multi-sensing capability. We would like that to be simultaneous, if at all possible, because we want to measure the state of a system in time, over time. So that's the real-time capabilities. And then we need to transfer the data. So that means we also need to have efficient communication subsystems. And we need to have local high-performance processing capabilities. These problems are generally non-linear. They are quite involved in terms of the mathematics. So if we don't have the computing capabilities accessible, then the results will be not necessarily in real time. So what do we define as optical profiling? And you will see some schematics about it later on. For us, optical profiling means using a broadband source and looking at all the modes of interaction of light with matter. Extracting that information and either putting it in the context of data sets or putting it in the context of parameters that we extract from the information that will define and classify a particular system. So that's what we define as optical profiling. So our proposed solution from the research point of view and from the commercial point of view is the use of miniaturized fiber optics-based multidimensional spectroscopy analysis. That's what I just described. Sensors that are integrated with sample preparation or separation in microfluidics modules. When you're looking about analyzing particulates, the mere process of sampling stream may induce classification. So therefore, we want to understand that what we're presenting to the spectrometer is representative of the process itself. But we also want to take advantage of the synergy between sampling and measurements, so that we sample appropriately and take advantage of the measurement capability for the sampling process. And also the fluidics behavior through the measurement module that would enable us to take measurements at different points through the separation and classification strategies that we follow. So we conceived a modular approach where the modules are designed with sensing requirements in mind. So we're not just going to design a spectrometer that has high sensitivity. We're going to design a system that takes advantage of all the characteristics to extract the maximum amount of information. The sampling and the sample preparation can be customized to the problem. So if we have a modular system, then we can meet the customer or the process needs or the environmental needs. And the sensing capabilities can be tailored to maximize information. You don't need all the information all of the time, but you have to be able to select information that you need to address your problem. There are advantages, commercial advantages to our approach. One of them is, of course, from the point of view of design. It's easier to remove parts than to add parts once you have done the engineering for it. Cost, simultaneous measurement of relevant variables. That addresses one important problem in all disciplines, which is the data reconciliation. If you use two measurements of molecular weight based on two different principles, right, the principles themselves are going to dictate what type of average you get of the molecular weight or of the particle size. And then you have an issue of data reconciliation. Which one are you using? Are you using a Stokes-based diameter, or are you using scattering-based diameter, or what have you? And that in turn affects how you calculate your concentrations, et cetera, et cetera. So the fundamental understanding of the measurement principles and how they are integrated within the system is important as well. And there are ample opportunities to generate and create projects in each and every one of the areas that I'm going to be discussing. So we strive to get the simultaneous measurements within the same device. That means that we're looking at the state of the sample. We also like to strive to use integrated interpretation models, so that the concentration that you measure with one type of, let's say in the near infrared, is the same concentration that you measure in the visible, and is the same concentration that you measure in the UV. So if you have your theory that links all of those spectral regions to the same parameter, then you can increase the reliability and minimize the data reconciliation problems. We realize also that multiple measurements, especially when you're talking about light, includes any interaction includes most of the effects. Commercial instrumentation in instrument manufacturing has sort of emphasized one variable at a time. But in fact, you have all of them. If you accept that fact, what you're going to have are two things. You're going to have complementary information, but you're also going to have redundant information. And that's not a bad thing, because redundancy increases the value of your statistics. So by taking this multi-sensor approach, we do these two things. We increase the number of variables that we can measure, but we also increase the value of our statistics. We want the instrument, for commercial reasons, to be able to be used both in the lab and in production or other environments. Why? Because if you have all your instrumentation based on the same measurement principles, then you make your life a lot easier, just from the point of view of reporting. We've been involved with the pharmaceutical industry quite a bit, and for them, the QC is critical. So that's part of our approach. And finally, if we have a miniaturized modular system, then we also wanted to be able to plug in and take advantage of other complementary techniques to, again, maximize the information that we want from the system. So just in a cartoon form, light interacts with matter in many ways. Absorption, reflection, refraction, scattering, transmission, excitation. So if we design a system that can capture many of these simultaneously, then we have a very powerful device to analyze the particulates that we're interested in. So what we have done is we have optimized the capture and interpretation of a fluorescence, absorption, scattering, angular scattering, reflection in a single device. And that's the prototype that we would like to bring here to the university to now do the fundamental research both on the materials and continuous on the optics. So we use a broadband source, we pass it through our material. Our material is going to interact, depending on its complexity, on many different forms. with a light. Then it's going to give us a signal. We have a multidimensional spectrometer that captures all of those modes of interaction and produces a multidimensional spectrum. Then we have the algorithms and the optical profile libraries that will then enable interpretation, identification, and quantification of these particles. And again, each and every one of these steps offers possibilities for fundamental research. One of the advantages that we have with our approach is that we sort of steered away from the traditional analytical chemistry methods. Not in the sense of the methods themselves, but in the sense of the approach, because we are taking a systems approach. We are trading off and trying to understand the characteristics of the system through the system manipulation and the measurement. So two examples here that I've shown before. This is the spectrum of normal healthy blood, as it is defined in the blood panel. This is a typical growth curve of a bacteria. If we use the standard statistical methods, we would be out of luck in terms of being able to interpret this reliably, because the natural variability of the normal healthy blood is such that if we just take the mean and calculate the standard deviations, there is very little that we're going to be able to tell about it. So what we have done instead is to decompose this in its fundamental building blocks. In the case of blood, will be the size, the hemoglobin concentration, the thickness of the membrane, the shape, the orientation of the particles. And you can address all of those theoretically, and this is what we have done that in our models and continue to do. This is a very active area of research and development for us and in general. So we account for both the theoretical and the statistical factors. The theoretical components, such as the size, the shape, the orientation, the composition, the internal structure, can be accounted theoretically. We also look at the fluid structure, because as you change the concentration, particles are going to interact. So we need to look at the intermolecular interactions, like in protein-protein interactions, particle-particle interactions, but also the hydrodynamic interactions. If you are measuring these things on their flow, then we need to understand if we have enough shear, our particles are going to be aligned. And how they are going to be presented to the spectrometer is going to determine the values that we obtain. We also look at the sample issues, as I mentioned before. One of them being very important, sampling integrity. But the other one is representative sampling. What is the effect of the background, the growth media that will give us these differences in spectral features? Now, we have the advantage that modern instrumentation has advanced, especially in the sense of detectors, and detector sensitivities has advanced tremendously. You can now get spectrometer systems that have a 3,000 to 1 signal-to-noise ratios. So that means that you can, not only the overall information is available to you, but as you zoom in, you can tailor your optimization algorithms to get the fine detail of your spectral features. So, and that is it's very exciting. We've demonstrated this over and over again, much to the surprise of many that are used to looking at broad spectra like the ones I presented. So, I mean, this is not just an idea. This has been certainly the work of my professional life, and has taken something that is very important here in marine science, and that is the interdisciplinary approach in the systems view. Because if you just look at one variable, you're going to be surprised when other interactions come in. And we looked at the intersection of this set of knowledge, the scattering knowledge, the multi-wavelength absorption, the management of biological fluids, the mathematical infrastructure that is necessary to solve the problems. And of course, the statistical analysis, not only from the chemistry point of view, but also from the biological point of view. So we also have had very powerful collaborations, among them Los Alamos National Laboratories, that have tremendous infrastructure. But most of all, it has been the interdisciplinary approach that gives us a view, a horizon, and then we focus in on the problems that need to be addressed. And also, we try to capture the synergy from the hardware, the software, and the information that is available through the optical libraries. So our research program, as I mentioned at the beginning, is focused on essentially three things: hardware, software, and the development of optical profile libraries, which is really materials science. So all applications are built on these three core elements. The hardware that addresses the sampling, the sample preparation modules, the multidimensional spectrometer platform that currently has multi-angle, multi-wavelength in this range of the electromagnetic spectrum, fluorescence and polarization. And the reason why we focus on those at the beginning is because they also impact the commercial value. And not only they impact the commercial value of our platform, but also enable us to establish barriers of entry for others to compete with us. So all those considerations were into designing the system. So for example, you can see here that if you have particles of different shape, the spectral features of the angular versus in wavelength spectra change dramatically. So you can then, from that information, translate it through the software, which are the models, into the shape and orientation of the particles relative to the detector. So the software includes the quantitative interpretation models, which are varied. The theoretical interpretation models enable us to establish cause-effect relationships. What is the relationship of the size relative to the signal? The shear rate relative to the shape, etc. And then the proprietary optical profiles that enable us to build our databases that we can use for identification and detection. And essentially, what we have done is taken a very simple approach and decomposed a complex particle such as a microorganism into its main scattering and absorption components, and then put it all together and end up with a model that we can use for quantification.
You should have a capital D, though.
I'm sorry?
You should have capital D in the formula.
Yes, I should. So the hardware integrates the analysis capabilities into a single system. And as I mentioned before, it's modular. We have our reagent delivery module, a fractionation and dilution module, sampling module. All of these are under development. We have the first generation, really, that has been integrated. The measurement and quantification module. And of course, in terms of our applications, we need a waste disposal module for many of the medical applications and environmental applications. And of course, our measurement platform. We are considering a variety of technologies, and we are testing all of them because not a single one will work for all instances. So one of them, for example, is an ultra micro centrifuge that is about this size, that can separate, in this case, in this particular case, we were interested in red blood cells and white blood cells separation. We also use acoustic and hydrodynamic focusing techniques, and I'll give you an example of that. Microdialysis and microslice exclusion. This is to fractionate the particles so that we understand. Every time we take a dimension off, it simplifies our mathematics in the optimization process that we're following. This, oops, now I don't know how to do that. I need to click in the, can you help me out? I need to click in this. We do that with what? With
Page down.
Page down? I don't see the mouse.
Yeah.
Oh, okay, here it is.
Doesn't work.
Let me. It's not working?
Is the animation?
Yes. Oh, there. I think it will work. So what you're seeing here is one of our designs for the chip. This is a red particles about the size of red blood cells in a green fluid. And there's a boundary layer here and a notch in this channel on the boundary layer. This is the main process fluid. Here is the